All right, welcome to the deep dive. Today, we're tackling a really interesting paper that's making some waves in text-to-image generation, the core breakthrough. It's essentially about getting these models to, well, think before they actually generate an image.
Right, a reasoning step.
Exactly. This paper, ImageGen-CoT, enhancing text-to-image in context learning with chain-of-thought reasoning. It introduces this structured process before image creation. And the performance jump, it's pretty significant.
Yeah, really significant.
We're talking up to an 80% improvement for their SeedX model on these tricky in-context learning tasks. So if you're deep in AI research or ML engineering, maybe wrestling with generating images from just a few examples, this deep dive is definitely for you.
Yeah,
We're
absolutely.
going to break down how it works, why it matters, and what it might mean moving forward.
Sounds good. And it builds on these unified multimodal LLMs, right? The ones that handle text and images together. But even these really advanced models, they kind of hit a wall when it comes to truly grasping the context in what the paper calls text-to-image in context learning, or T2I-ICL.
T2I-ICL. Okay.
Yeah.
That's where you give the model, say, a couple of text image examples, then a new prompt, and you hope it figures out the underlying theme, the style, whatever.
Right, like it learns on the fly from the example.
Exactly. And the paper really digs into why that's hard and offers this ImageGen-Q as a compelling solution.
Okay, so let's make this T2I-ICL thing super clear. The paper uses a good analogy, or maybe I'm adapting it slightly, but imagine showing an AI a leather-bound book, image pair 1,
Okay.
then a leather apple, image pair 2. Then you ask it to create a box.
Right. Our brains immediately jump to a leather box.
Instantly. We see the pattern, that shared leather quality, but as this paper points out, and you can actually see it in their figure 1, with the baseline SeedX results, current MLLMs often just, well, miss that.
They fail on that contextual consistency. Yeah, you might just get a regular cardboard box. It doesn't carry over the leather style. So this paper is all about bridging that gap, that sort of intuitive reasoning humans do.
And they use a specific benchmark to test this, right? The Cove SAA Benchmark.
That's the one.
Yeah, it's designed precisely for this, evaluating how well models adapt to new generation tasks based on just those few examples in the context. They also mention Emu2's work using DreamBench for subject customization, which is a similar idea.
Binding visual concepts from reference images.
Exactly. Both really highlight the same core challenge, getting that intuitive leap, that contextual understanding.
So how does ImageGen-Go actually fix this? They introduced this framework.
Based on chain of thought.
Right. If you follow LLMs, you've probably heard of chain of thought prompting. It's like asking the model to show it's working out step by step before giving the answer.
Improves reasoning on complex text tasks.
Hugely. And ImageGen-Go basically takes that idea and applies it before image generation. It forces the model to articulate a thought process about the context first.
Like it has to say, okay, I see leather here and leather there, so the next object should probably also be leather.
Exactly that kind of reasoning.
Yeah.
Figure 3 in the paper shows this two-stage inference protocol they use.
Yeah, it's quite neat. Stage 1. The model gets the input, the examples, and an instruction, and it generates the ImageGen-CoT reasoning chain. Let's call it R.
Okay, the reasoning chain R.
Then stage 2, it takes the original input, X, plus this new reasoning chain, R, a specific image generation token, and then it produces the final image.
So the reasoning R becomes an explicit input for making the image.
Precisely. It's not just an internal thought. It directly guides the generation.
And what really jumped out at me was that they mentioned they tried just prompting for CoT first, like in one go.
Right, like just asking, reason about this and then generate the image.
Yeah, but it didn't work reliably. The images were still off and off. That's why they landed on this specific two-stage approach.
It suggests, doesn't it, that simply having the reasoning ability isn't enough for reliable visual output in these tricky cases.
You need to structure it and explicitly feed it back in.
Yeah, you need that mechanism to translate the understanding into the pixel, basically. This two-stage process provides that structure.
Okay, but then there's the challenge of getting good reasoning, right? Because the models might just generate vague stuff or nonsense.
Exactly. Unstructured ramblings, as they put it. And that's where their automated dataset construction pipeline comes in. This is, I think, a really crucial part of their work.
How does that work?
It's pretty clever, actually. Figure 3A shows it. They automate the creation of a high-quality data set of these ImageGen-CoT examples.
Okay.
So first, they grab T2I-ICL instructions from existing data sets. Then they use powerful MLLMs like InternVL 2.5 for DreamBench plus examples, and a self-consistency method for Cove SAA to generate the actual step-by-step reasoning, the ImageGen-CoT, and the image prompts.
So they use other AI to generate the training data for the AI they're improving.
Essentially, yes. And they even use another model, FLUX-1 Schnell, to generate detailed image descriptions to guide the diffusion models for better image quality.
Wow, okay. That's quite a pipeline.
But the really neat part is the iterative refinement. They don't just generate once.
Ah, okay. What happens then?
The model generates multiple prompts and images. Another MLLM acts as a critic, picks the best one. Then another MLLM critiques that chosen image, identifies flaws.
Like at Are Critic?
Sort of. And based on that critique, the prompt gets refined. And this loop generate, select, critique, refine continues until the image is good enough or they hit a limit.
That sounds intensive, but I guess it really boosts the quality of the reasoning examples.
It does. The data shows it works. Table S3 in the supplement shows clear gains from this refinement, like 1-2% on Cove SAA and almost 5% on DreamBench plus metrics. It's not just about more data, it's about refining the quality of the reasoning.
So you end up with this data set of paired reasoning chain high-quality image examples.
Exactly. Ready for fine-tuning.
Which is the next step. Figure 3B shows the training pipeline. They took models like SeedLlama and SeedX and fine-tuned them on this curated data set.
The goal being to teach the models to do this kind of structured reasoning internally, to make it part of their process.
How did they structure the training?
They actually split the dataset use into two parts, primarily focusing on the first. Part 1 trains the model to just generate the ImageGen-CoT reasoning itself. Input examples and a prompt for CoT output, the reasoning chain. They use standard language modeling loss for this.
Just predicting the next word in the reasoning.
Pretty much. The second part trains the image generation. Input is the original stuff plus the generated CoT, and the output is the image. The loss depends on the model, like visual tokens or embeddings. But they stress that the main focus and where they saw huge gains was improving the CoT generation using that first split.
And the results after this fine-tuning, you mentioned the 80% earlier.
Oh yeah, the gains are quite startling. Tables 1 and 2 show it clearly. SeedX, fine-tuned just on that first part, the reasoning generation part, improved by 88.5% on Cove SAA.
88%. Just from getting better at reasoning before generating.
Exactly. And on DreamBench plus A, it was even higher, like 114% improvement. Even using the full data set, the gains were massive, just slightly less. It really hammers home how critical that reasoning step is.
Wow, okay. But they didn't stop there, did they? They looked at boosting performance even more at test time.
Right, test time scaling strategies, kind of like the best of N ideas you see elsewhere. Figures 3C and 4 cover this. How can we squeeze even better results out during inference?
What strategies did they try?
They explored 3 main ones. First, single chain scaling. Generate one reasoning chain, then create multiple image variations from it just by changing the random seed for generation.
Okay, one thought, many pictures.
Yep. Second, multi-chain scaling. Generate multiple different reasoning chains using higher temperature decoding to get variety and then generate one image per chain.
Multiple different thoughts, one picture each.
Exactly. And then the third, which combines them, hybrid scaling.
Best of both worlds.
Seems like it. Generate multiple different reasoning chains, and then for each of those chains, generate multiple image variations by changing the seed.
Okay, multiple thoughts and multiple pictures per thought.
You got it. And figure 4 shows the results pretty clearly. Hybrid scaling consistently comes out on top on both benchmarks.
Better than just generating more images from one reasoning path, or more reasoning paths with one image each.
Yeah, interestingly, they found that generating diverse reasoning paths, the multi-chain way, was about as effective as just varying the seeds from a single chain. But combining them in hybrid scaling leverages both sources of variation reasoning diversity and generation randomness.
That makes sense.
And crucially, they compared this to just taking the original SeedX model, the one without ImageGen-CoT fine-tuning, and just generating more samples from it. It didn't come close. Even the basic scaling with ImageGen-CoT outperformed just cranking up the sampling on the vanilla model. It really highlights that the reasoning itself is the key improvement, not just brute forcing more outputs.
Okay, let's talk qualitative results. Seeing the images helps understand the impact. Figure 5 has some good examples.
It does. You see the CopySat lace book example again. The baseline SeedX might make a book, but misses the lace. With ImageGen-CoT prompting, and especially the fine-tuned model, it gets that intricate detail.
And the Dreambench ++1, the sad egg in garden.
Yeah, the baseline struggles. Maybe an egg, maybe a garden, but sad. Forget it. ImageGen-CoT helps it understand that complex combination. The object, its emotion, and the setting.
It's inferring those implicit things and handling the composition better.
Precisely, which ties into their hypothesis. Better understanding leads to better generation. Table 3 supports this too.
How so?
They tested the models not just on generating the image MG mode, but also on generating a text description of what the next image should be, TXT mode.
Ah, testing comprehension directly.
Exactly. And they found ImageGen-CoT significantly boosted performance in that TXT mode. The models got much better at describing the target image. And those text comprehension gains correlated strongly with the image generation gains.
So proving the reasoning actually leads to better understanding, which then leads to better pictures.
Seems to be the case. It's compelling evidence.
So wrapping up the main discussion points for the paper, they really identify two big hurdles for this T2I ICL stuff.
Yeah. First, just comprehending the instructions, understanding the pattern from the examples. The baseline model's relatively poor text generation performance shows this difficulty.
They don't quite get the task just from the example.
Right. And second, even when understanding improves with ImageGen-CoT, there's still a challenge in translating that improved understanding into a perfect image. Image generation sometimes lags behind the text understanding gains.
The generation part itself is still a bottleneck, even with better reasoning.
Exactly. These are important takeaways, suggesting future work needs to tackle both comprehension and the reasoning to image translation.
Okay, so boiling it all down, the core message here is pretty clear. ImageGen-CoT, adding that explicit, structured reasoning step before generating the image, it just works.
It significantly improves how these big multimodal models handle text-to-image in context learning. That think-then-generate paradigm seems really powerful here.
And the paper gives us, what, 3 main contributions to unpack?
Yeah, I'd say. 1, the ImageGen-CoT framework itself, this 2-stage approach. 2, that really smart automated pipeline for creating the high-quality reasoning data set.
The iterative refinement part was cool.
Definitely. And 3, exploring those test time scaling strategies, showing that hybrid scaling gives the best results by combining diverse reasoning and diverse generation.
And those performance numbers are hard to ignore. Up to 80% boost for SeedX is just massive. It really shows the potential here for making these models much better at complex contextual tasks.
Absolutely. It opens up some really interesting questions for what's next,
Like what? What should people be thinking about?
Well, how can we refine the reasoning itself? Make the ImageGen-CoT even more effective or efficient? Could we maybe apply this whole reason-first idea to other multimodal tasks, like video generation or text-to-3D?
That's a great question. Does reasoning before acting help across the board? And what about the practical side?
Right. What are the computational costs? That hybrid scaling sounds powerful, but is it practical for real-time applications? Latency, cost, those are big factors.
Definitely food for thought. If you're working in this space, AI research, multimodal learning, text-to-image, this paper seems like a must-read.
Agreed. Lots of insights in a promising direction.
Well, thanks for joining us for this deep dive. Hopefully that gives everyone a good handle on ImageGen Code.